Okay, my name is Joachim, but everyone calls me really Kim. I work at Stanford University, where I'm a postdoc, and I'm going to talk about pivoting with RethinkDB. And when I say pivoting, I mean something that appeared in a Dilbert blog entry recently, where he talks basically where startup companies have to reinvent themselves quite quickly in order to have, at some point, a product ready which they can sell. And that's a lot how we work in research as well. Okay, so what we do is we work in biomedical sciences, bioinformatics. That's dealing a lot with drugs, genes, diseases. And we do drug repurposing, where we basically look if we can use certain drugs to treat diseases which they weren't designed for. We also try to improve the treatment of diseases. And we do a little bit of drug discovery, where it's basically we look at chemical compounds, biological pathways, and stuff to discover new knowledge that can help you to treat diseases better. So we have a big problem, and the problem is scientific data. Because scientific data is mostly heterogeneous. That means if you take two data models, let's say you have one data model from one data provider, which is about disease, and then from another data provider, these models don't match up at all, right? And you have the same problem for drugs, for genes, for pathways, and there are a lot of data providers. So you're dealing with a lot of different kind of data. Well, the data is sometimes similar in what it is, but how it is being represented is a lot different. Then the data itself, the data structures, are changing a lot as well. So that's the typical research thing where different people work on the same database. So sometimes when you get a new version, all the data models change completely, right? That's a disaster for your scripts which you're working with. Then we have also a lot of sparse data, which means someone does some study on something, like a tiny minor thing, like a very special disease, and then adds this information to the database, but it's only annotating like very few data items, and you have to deal with that. And then we also have kind of big data. I don't know what big data means for guys here. For us, it's usually in the terabytes, and that comes usually when we get stuff from sequencing machines like DNA and things like that. So these are the technical problems. Then we also have like a conceptual problem, where in research we don't really have a business plan, right? How it works is we have some kind of hypothesis which we think is true, and we have sort of an action plan how we try to tackle that, but most of the time it doesn't work, and that's when the pivoting comes into action. So we try something, it fails, we rinse and repeat. And that's basically from the Dilbert comic where he talks about the pivoting. That's what we do a lot. So even though we write grant proposals where we pretend we know exactly what we are doing to get money, to get researchers being paid, that's not usually how it works in real life. In real life, we have to reinvent what we are doing quite a lot, and then try to solve whatever we claimed we would solve in the research proposal. And we also have a really hard deadlines which we have to work against. So I'm not sure. Some people think they are soft and hard deadlines. I think they are just deadlines. And for us, it's unquestionably that they're hard, because a funding agency will just give you money, let's say, for 5 years, and that's it. After the 5 years, you have to write up what you did, and there will be no more money. You can't ask to get another year extension or something like that. So how it usually works in research is it's really purgatory. There are a lot of temporary solutions where basically, as you reinvent yourself, you come up with a lot of bash scripts, and you do set and awk and grep and all this kind of stuff. And you kind of throw it together in a lot of scripts and then try to solve your problem like that. But that gives you a reproducibility problem, right? Because if you have a lot of scripts lying around somewhere on the file system, no one is going to reproduce whatever you did, because no one knows how to run these scripts. There's usually no documentation, which means code maintenance is pretty much impossible. And the data we are dealing with, sometimes it's in an SQL database, but it's already denormalized for performance reasons. You never see really the original data, which would ideally be normalized and use foreign keys, primary keys, stuff like that. So that's the stuff you usually never get to, because you're already working with some optimized database. Then a lot of stuff is text files, CSV and TSV files. So you have no information about the data you're actually seeing. So you don't know if if a certain column, if it contains numbers, if that's always the case, or if sometimes also strings in there. If you're dealing with foreign characters, which is sometimes the case, well, good luck with that. You're not going to solve that because there are all these different character encodings, and not everyone is using UTF-8. And then there's Excel as well. And it's so bad that people actually have scientific publications where they point out how bad it actually is, because it mangles up your data, right? A lot. And then you get, well, weird results. So our approach is to make a little bit more sense of all this stuff. And what we do is we take our input data, which is all these different kinds of file formats, and we translate them into RDF, which is a semantic web data format. Who has heard of the semantic web? Okay, a few people. I guess a few people of RDF. Some people, okay. So don't worry, it's just, let's just call it another data format, which is kind of annotating your data with types and stuff like that so that you can make more sense of it. It's very similar to how you actually program stuff, where you have your data model at different classes for different things and stuff like that. It's basically you're taking an object-oriented programming approach and apply it to data. That's essentially all it is. So we also get semantic annotations because of that. That means we know what we are looking for. So if there are diseases, we know that's a disease. And if there's a gene, we know it's a gene. If there's a biological pathway, we know what it is. It also means we have a knowledge about linked data. That means we know where to find us. So linked data is basically just having a URI for every data item. So you don't only know that you're having a gene somewhere, you also know where to find it. So basically URI goes back to the data provider, and then you know where it comes from. And it also tells you how data is related, where you have, for example, let's say a disease and a gene, and between that you have a URI which links them together as well. So that's how the semantic web stuff works. Our data is also discoverable, and we have actually proposed a W3C node, which is almost ready. We are just going through the last stages where we're trying to get it past the W3C HTML validator, and they also do some semantic validations. We are fixing that. They're very picky on that. So that's basically how we approach this thing. So what about the technology? So there are databases which work with RDF data, and they're called triple stores. But these triple stores are not always fitting our use cases. If you don't know what a triple store is, think of it as a SQL database. It's similar-ish. So there's RethinkDB, and it comes to our rescue. So we use RethinkDB for all our data so that we can do data integration and unification. And what we do is we take these semantic web formats and we translate them into JSON LD. The LD stands for linked data, and it's basically just another representation or a specific JSON format that is able to hold the data which you have in RDF. Basically, it just defines some namespaces and stuff like that. The key point here is that you have JSON documents, essentially, which you can work with. And the great thing about RethinkDB, what I like, is that it interfaces with Ruby and Python. So most of my scripts, analysis scripts, are in Ruby, and I'm transitioning to Python now. And there are a lot of frameworks already for biomedical and bioinformatics research. And they are called BioRuby, BioPython, SciRuby, SciPy, and NumPy. And I can use all these analysis frameworks already. And they integrate nicely with RethinkDB because RethinkDB supports Ruby and Python, right? So that's the thing how we integrate RethinkDB and the little figure down there. So we take all these weird file formats, we just put them into RethinkDB where they become JSON documents, and then I run my analysis scripts and visualization on that, basically. And what convinced me to use RethinkDB is basically it's easy to administer. So beforehand, I've been using MongoDB and a little bit of Couch. They're okay, but RethinkDB is better. And it's really a lot easier to use. Yeah, yay! And I found RethinkDB is really fast, flexible, and scalable. Like as it was demonstrated, like the sharding, so amazing that I can enter the number there and click a button. I mean, how awesome is that, please, right? And it's perfectly suited for our scientific analysis workflows, which are sometimes called analysis pipelines. And that's essentially the query chaining, which Slava talked about. And that's essentially how our analysis works. So we have, let's say, at least one table, and then we have one step to get some data. Then we filter on the data, then we reduce it somehow, and then we filter a little bit more, and these steps carry on. And that's essentially how all our research stuff works. There's some more complicated stuff in between, but essentially that's how research analysis pipelines work. And RethinkDB exactly goes for this query pipeline model, right? So we can directly translate our stuff into RethinkDB queries. So where we want to go next is we want to be ahead of the game with RethinkDB and JSON-LD so that we can actually publish first, and that means we get more acclaim. It's always when you're first in research, well, it's better, right? I guess it's a lot like in businesses. When you're first on the market, you essentially win, right? And we want to save time and money. So we have, scientists usually have a little time to spare, and I want to improve that. I also like to document my code, so I need time for that, and that means I need a good infrastructure, which allows me to have the time available to write my documentation so that the next guy after me can actually pick up where I left. And research is publicly funded, so we actually save your money because we work more efficiently. We're always keen to work with collaborators, so if you're interested in contributing to the research, maybe have some visualization, JavaScript, library or something which you really want to get to show your customers or something like that, please come to me after this little presentation. We could plug it onto our website or stuff like that if it's cool enough. Thanks.